Welcome to this lecture of course Computational Hydraulics. We are in module 4 surface water hydraulics, and this is unit number 3 steady channel flow, channels in series or single one. What is the learning objective of this particular unit? At the end of this unit, students will be able to solve steady channel flow problems single or in series using implicit method. Although this implicit approach is not related to time, we will be talking about steady channel flow. Essentially, we will be talking about the solution of nonlinear discretized equations. In our last 2 lectures, we have discussed this gradually varied flow or GVF. In GVF, we have seen that we need to solve this dy by dx S naught minus SF 1 minus Fr square, this first order equation, and we have this initial condition x is equal to 0, we have y naught. If we solve this one, we can get the variation of y with x. So, from this one we can classify the type of GVF, but for classification further we need 2 main flow depths. One is YC, which is critical depth, and this corresponds to our critical depth line. So, if we consider this as channel and flow is from left to right. So, obviously, for this one if we have CDL or critical depth line here and normal depth line above, then we have M profile conditions, and we can find out this NDL based on the value yn. Yn is nothing but this is normal depth. We can calculate this normal depth from our Manning's equation. So, in last 2 lecture classes we have discussed the solution process. One is implicit and explicit and implicit set approach for GVF profile, the solution, and we have solved one initial value problem with one initial condition or one condition specified, only one at the one end, and what is the value on the other end that we do not know. Now, we will be talking about this continuity and momentum together, but we need to solve those 2 equations simultaneously, but for special cases we can omit one of the equations and continue with a single equation to get the solution. Let us say that we have a problem where we have a channel which is single channel, this is channel bed and this is the flow direction, and obviously this is flow depth at any location. So, this is single channel. Now, we can have situations where we can have multiple channels, but they are in series, they are directly connected. Let us say this is our first channel, this is second one, these are directly connected. If you see the top view of this one, so we can see that either the cross section is not varying, there can be situations where there will be change in the cross sections, but in this case we have considered that at this junction point depth on left side and right side equal, but we can have situations where if we have some hydraulic structure at this junction point, then there will be two different conditions on left and the right hand side. So, let us see how we can solve this problem. Now, first of all we need a governing equation to solve this problem, and we will try to solve this problem as BVP or boundary value problem, and we will need these nonlinear equations or the nonlinear equations will be generated as part of the discretization process, and finally we can solve this nonlinear equations using iterative approach for nonlinear equations. Now, let us see what is the governing equation. Now, this is boundary value problem. What is continuity equation? Continuity equation is dq by dx equals to 0. That means along the longitudinal direction there is no change in or the variation of q is 0. So, dq dx. So, in this case we will have another momentum equation d by dx, this is minus sf, and E this is the total energy. In this case y is the flow depth, z is the elevation head, alpha this is momentum correction factor alpha square, the q square divided by 2g a square, essentially this is v square by 2g. Now, if you replace this v with q by a, we will get this term. So, this is alpha q square by 2g a square. Now, in this case these are the terms, y is flow depth, SF this is friction slope. We can get this one from this expression where n is Manning's roughness, r is hydraulic radius, a is cross sectional area in this case, and z the elevation of the channel bottom with respect to datum, alpha this is momentum correction factor, q discharge, g is acceleration due to gravity. Now, we need to define certain terms. First of all, we will consider different channel reaches. So, this is one channel reach that is under consideration. Now, within this channel reach, if we divide it into number of parts starting from 1 to NL plus 1, NL is the number of segments starting from 1 to NL. here. So, these are essentially number of segments, and these red dotted lines, these are sections. So, we have channel reach, segment, section. Now, out of this all this total energy or E value is defined with respect to datum, this datum. Now, if you have a segment I, that means it is connecting the sections I and I plus 1. So, I is a section, I plus 1 is a section, I is a section, and in this case I is our segment number. So, this is the general notation that we will be utilizing, and channel reach number will denoted with this L. L is the channel reach number. Now, if we consider our general channel flow for the section I, for the segment I with the sections I and I plus 1, then we can define each term on that energy expression or E. So, first of all, with respect to datum, if we consider this section I, we have elevation head. So, this is elevation head, then Y L I, this is our flow depth, and on top of that we have kinetic energy head, or this is alpha L I Q L I square divided by 2 G A L I square. In this case this Q L I, this means that for Lth channel reach at ith section, what is the discharge. Similarly, area Li, this means at Lth channel reach at ith section, what is the area. Similarly, on the downstream end, this I plus 1 section, we have this Y L I plus 1, Z L I plus 1, and this is again our thing. In this case we have alpha I L I plus 1, this is Q L I plus 1 square divided by 2 G A square, again A should be at L I plus 1. So, with this we have defined different variables or parameters for these two sections I and I plus 1. Now, this top surface is representing AGL or hydraulic grade line, and this top one is representing energy grade line. Now, in this case we can see that there is difference between this point and this point. This is essentially the average of the friction slope multiplied by del XL. Del XL is the distance between these two sections, and in this case we will consider uniform del x for a particular channel reach. Now, for discretization we will consider this continuity equation, and if we consider the ith segment of the lth channel reach, then this is dq by dx. This dq by dx essentially we are considering at ith channel reach only, ith segment only. Now, for this case we can get this discretization q l I plus 1 minus q l I divided by del x l, this is equal to 0. Now, we can utilize this information during our solution process. Now, L index for channel number and I index for different sections within a channel reach. Now, in simplified form, for ith segment of the lth channel, we can write directly from this expression that q l I plus 1 and L I, these two values are equal. Now, for single channel, that means if we consider any channel L, for that channel we can have multiple sections, but if we consider the discharge QL for or inlet discharge for this channel L, then this QL1 at section 1 to NL plus 1, NL plus 1 is the total number of sections for this lth channel reach. So, this is equal to QL. So, for all sections or discharge is equal, and NL is the number of segments for this case. So, in this case we are considering NL plus 1 number of sections. Now, if we consider channel in series, then also the situation will be same, because if we consider two channel sections, let us say this is our first one and this is the second one, 1 and 2. In this case we will have inflow discharge some Q1, and in this case if we consider this discharge is Q2. So, obviously in this case this Q1 should be Q2. Now, discretization of this momentum equation, again we will consider the discretization for the channel segment. So, this is d by dx at I, we will consider that and that thing here. Now, if we consider this discretization here, we can use simple our forward difference. So, we are getting EL I plus 1 minus EL I divided by del x L. L is the channel reach number, and minus we have SF in the right hand side. So, we can get SF I value at channel section I and SF I plus 1 value at channel section I plus 1. So, if we take average of this two, we can represent the right hand side term. So, further we can expand this. So, expansion is done by putting E equals to y plus z alpha q square 2g a square. Now, in this case we can see that we have number of terms available here, but if we closely consider the parameters and different variables, we can easily identify the unknown variable. So, unknown variable in this case is y, because for channel single channel or channel in series we have constant discharge condition, and discharge is also not varying with time. So, we will have a constant value of discharge for all channels, and those values are equal. So, in a particular problem, Z is known, Q is known, A which is again function of y, in this case also y unknown, Z is known, only unknown is y, and A is a function of y only. On the right hand side we have another value of this hydraulic radius, which is again function of y, and we have discharge value constant n, which is Manning's roughness coefficient, that is also constant. So, in functional form this is again nonlinear equation. So, we can write it in functional form for solution, because we need to utilize Newton-Raphson technique. For Newton-Raphson technique, first step is that we need to represent it in terms of some f phi where phi is a vector equals to 0. So, this expression we need to generate. So, for any segment we will get this Li MLI or momentum Li function, and this should be equal to 0, and this thing is valid for 1 to NL number of segments. We have NL plus 1 number of sections, but NL number of segments. So, these equations will be there for NL number of segments. Now, in reduced form, because we know that for single channel we our channel in series we have constant value of QL. So, we can take out this QL square out of this right hand term. Now, we can define two parameters, because these are channel reach dependent parameters for our case, and R and A, these are functions of y, this is again a constant term for 2 consecutive channel sections. In this case, now we have NL nonlinear equations with NL plus 1 unknown flow depth. In this case, if we consider a single channel, then we are starting from 1 and going up to NL plus 1, but in this case we are generating MLI equations for segment 1, segment 2, segment 3 up to NL. So, we will have in NL number of nonlinear equations like ML I equals to 0, but we have unknown flow depths for all nodes. So, this is node 1, 2, 3 up to NL plus 1. Now, we need one extra equation to solve this particular problem. So, one condition that we can utilize for subcritical flow, that is at the downstream end we have specified depth condition. So, dBL that means downstream boundary condition for Lth channel reach at L plus 1 segment, this is equal to YL NL plus 1 minus YD. YD is specified value at downstream end, but if we have supercritical flow condition, this will be YL1 YU, that means at the starting of the channel or at the first section itself our depth is defined, then we will have this upstream boundary condition. So, upstream boundary L N L plus 1 because we already have NL number of equations, this is NL plus 1 number equation in this case. So, YL1 equals to YU, this is for downstream boundary, this is for upstream boundary condition. Now, we already have our discretized momentum equation. In this case we have for each of those equations we have 2 unknown variables, one is YL I plus 1, another one is YL I. So, for solution process using Newton-Raphson, we need to find the coefficients or coefficient matrix, which is again a Jacobian matrix. Now, in this case by assuming this term as C1, this term as C1 and this second term as C2, we can reduce the size of this equation, at least in compact form we can represent this. Now, with this compact representation, now we have all the variables on this right hand side of the equation, and R A, these are variables of y L I plus 1 and y L I. Essentially in this case R L I plus 1, this is function of y L I plus 1. Again area L I plus 1 is function of y L I plus 1, and this hydraulic radius at L I, this is function of L I. A L I is function of A L I. Now we have these terms in our equation. If we take a derivative to get the coefficients or elements of the Jacobian matrix, then from our momentum equation we will get two terms, because we have two variables. So, one is corresponding to y L I, another one is corresponding to this y L I plus 1, and C1 C2, these terms have already defined. Now in this case for any general prismatic cross section, we need to find out what is this dA by dy, and it should be evaluated at L plus 1. Similarly dr dy Li index, this is dA by dy at Li. Similarly for the second term we will have dA by dy at Li plus 1 and dr by dy at Li plus 1. For general channel cross section, this dr by dy, this is dr by dy, this is T by P. T is the top width of the channel, P is the weighted perimeter, R is hydraulic radius divided by again the weighted perimeter, dP by dy in this case. Now for subcritical flow, again in case of subcritical flow we have seen that the condition is y L n L plus 1, this should be equal to y d. If I transfer this y d on the left hand side, this is 0 and this is our downstream boundary condition, or dB L n L plus 1 equal. Now if I take derivative with respect to first y L n L, so I should get 0 here, and in this case I am getting 1 because this is only y L n L plus 1. Now for supercritical flow condition, similarly if we have this y L 1 equal to y u, and we can transfer it on the left hand side upstream boundary L NL plus 1 equal. Now, in this case if we take derivative with respect to y L 1. So, obviously, we are getting 1 here, and for second term we are getting 0. Now, in general form the governing equation including boundary condition can be written as this coefficient is there, the coefficients which we have calculated for our Jacobian matrix, and D this delta Li and delta Li plus 1, these are the increment values. Now, in this case this del m Li this is again second term in the Jacobian matrix, and these are the equations. So, starting from 1 to NL segment we have this equation. This is the thing that we can directly solve, but we need another boundary condition here, that is subcritical flow condition. In this case coefficient is 1, that is why I have not written that. Now, after getting the solution through iteration, at every iteration we need to update the values. So, update thing we can do like this y L, that means y L vector at pth iteration, this should be calculated at y L p minus 1, y L p minus 1, and this minus sign is already there. So, if we get some solution out of this, so we should add this directly. So, this is again based on the values at p minus 1. So, after getting the solution for this del values here, we can add that value with the guess value or previous iteration value, and we can get the updated value, and we can iterate it until and unless we get the convergence for Newton-Raphson method, and finally we will get the solution. So, what is the matrix structure? We have I plus 1 in this case. So, we have one diagonal term and another one which is banded one, and the green one is that, and the last dot is for the boundary condition that will be utilizing for our case. Now, for supercritical flow condition the situation is same, but in this case we have the first condition available here or the condition which is available at the first section. Now, the structure is like this. In supercritical we have this structure of the matrix. Now, if you have channel in series, obviously our discharge will be same for both the cases, and we need to satisfy the energy condition at junction point. Energy condition at junction point. Now, if you have two z values available for this section, then for these two channels at this section. So, we can consider that z values are different, otherwise if both the points are the same points, we can neglect this elevation thing and we can just equate the flow depth here. Now, let us consider a problem where we have a given cross section type rectangular B, which is the width of rectangular section, that is 15 meters, G is 9.8 meter per second square, S naught which is 0.0001, Manning's roughness 0.015, Lx is 200 meters, Q is 20 meter cube per second, and Yd, which is depth at the downstream boundary, is 0.6 meters. Now, required is estimate the flow depth across the channel reach. Now, this problem is similar to our problem that we have solved in GVF case. In that case, the critical depth was around 0.567. Now, what is the downstream boundary condition here? This is 0.6. Now, it is just above the critical depth, and with this condition, if we simulate using this boundary value problem, so we should get similar profile in this problem also. So, if we consider this one, for rectangular channel, this dr by dy, this is b square by b plus 2y square, and top width is b. Now, we can utilize this information here. Now, if we take our Scilab, again I have written one code so that we can simulate this channel flow condition. So, first is 1D channel, this is single channel. Now, these information like q equals to 20, S naught equals to point, these are given information. I have considered m node equals to 201 like our previous problem that we have discussed in previous lecture class. Then epsilon max, this is 1 into 10 to the power minus 6, this is required for Newton-Raphson method. Global, we have constant discharge value S naught, N, B, G, these values are available. So, we can solve this. Now, what are these problem dependent parameters? Problem dependent alpha, we need alpha. For single channel, I have considered alpha equals to 1, xc which is Lin space between 0 to Lx, I have generated m node, that means m node number of nodes which is 201. This del x is Lx divided by m node minus 1, that means it should be divided by the number of segments. Now, z value, now z value is 0, I have considered that the end section from datum, and from there we can just add S naught into delta x to get the z value for other sections. Now, yv which is the variable, this is defined for m node, that means NL plus 1 number of nodes. Now, in this case we can define this C1 and C2, C1 and C2 these are constant parameters. Now, interesting to see that for rectangular channels area is by dy by dA by dy, this is b, r which is by divided by b plus 2y, and dr by dy we can directly calculate using this one. Now, we can define the equations for each segment. For each segment we need to calculate this MLI, this value is required for the right hand side for the solution process, and these two are dy by, this is dm by dy Li, and this is dm by dy Li plus 1. So, these two values are required for our calculation. Now, we can start with our Jacobian matrix, this is zeros m node, and our right hand side we have zeros m node 1. Now, with the count I am starting 0, RMSE equals to 1, and guess value I am starting from the downstream end value which is yd for all values or all sections. Now, this RMSE is greater than epsilon max, then only we should iterate. So, after entering into this loop I have used this RMSE equals to 0. Now, from there we are getting this I equals to m node minus 1, and ai I which is our diagonal term, this is dm by dy I, and ai I plus 1, this is dm by di I plus 1, and ri which is minus mli. Now, I have generated these equations and I need the boundary condition. Now, finally, I need to solve this delta y. After solving this delta y using a backslash, this is internal function of Scilab, I am utilizing it for del y calculation. Now, after getting this we need to update this yv. Simultaneously we can also calculate this RMSE value, and finally we can get the RMSE value and I count here. So, now if I use this xc which is the x coordinate, yv and yz, the zv are the z values for each each section, we can generate the GVF curve here. And interesting part here is that this is my bed profile, and this is 0.6, and again we are getting some value here. This is the value that we are getting out of this. And in this case upstream section we have value which is more than 0.9 or 0.95. Now, if you see our channel in series, we have rectangular channel And let us say that if I divide the same 200 meter length into two parts, 100 meters and 100 meters, with 0.004 to 0.008, we can get the flow profile there, or profile there, and both the cases N1, N2 values are this, and L1 is 100, L2 is 100, discharge is same because we need to utilize that, and YD, this is in the downstream 0.6. Now, what is there? If we see this channel in series, now in channel in series we have this discharge value channel CHL, we have two channel reaches, S0 we have two S0 values, N we have two N1 values, Lx we have two Lx values here, M node because we need to divide both the parts separately. So, we have M node for channel 1 101, M node for channel 2 again that is 101. Now, epsilon max 1 into 10 to the power minus 6, in this case S naught N these are varying, that is why I have not kept it here as global variable. So, Q, B and G, these three are global parameters here. Now, alpha I have considered 1 and 1 for both the channels, and YV this is some node, that is M node L or M node 1 plus M node 2. We have a total 202 variables because we have 101 nodes each for each of this channel reaches. So, in this case I can define this delta x. Delta x is again varying for L, L is corresponding to a particular channel, C1 is also varying with L, C2 is also varying with L. Now, we can define this MC which is the total number of nodes there, and we need those many flow depth values. In this case I can calculate the Z values starting from 0 value at the downstream end portion. So, if L equals to CHL which is the downstream channel, we can calculate the ZV or ZV value here. So, in this case we can calculate that ZV from there, and these derivatives are same like our previous one, but we need to transfer this C1, C2 and del x S0 values here because these are not constant values now. Again y C1, C2, y C1, C2 these are required here. Again some node, some M node into some M node here, or 0 some M node. That means if we have two channels 1 and 2, we have M node 1 and M node 2, then we can add this to those many variables we need to determine because we need flow depth for the channel length. So, in this case again we will consider YD which is the initial guess for our Newton-Raphson. In this case, first thing what we will do is that MC equals to 0, this is one counter here, and with this counter will create or add the values here. MC, and this is starting for channel L 1 to CHL, I 1 to M node, MC equals to MC plus 1. For after entering into this loop, we will add this MC or increase this MC, and this is CHL I node, IM node. So, for this one we need this condition, which is the specified depth here, and in this case we have one junction node. For that junction node, we need to satisfy the depth continuity, because we are not considering variation in bed. So, A MC MC, this is for any general element we are considering. Now, delta y we can calculate from AR, this is for some M node, and YV again we can update and calculate the RMSE values, and finally we can get the solution from this iteration process. So, if we see this value, again this value is somewhat near 0.9 in the upstream section, downstream it is around 0.6 or 0.6 exactly, and interestingly in this case slope is varying. So, initially it was milder, now it is a mild slope, and obviously we can see one change in profile at this junction point, but a continuity is there in the junction point. So, we have calculated or estimated the flow depths for different sections. Now, we have a framework in place where we can utilize the constant discharge values and maybe upstream or downstream boundary condition, depending on the flow situation. We can get the corresponding flow profile there. So, we have used this two codes, one is single channel steady 1D channel single, and channels in series steady 1D channels in series, and we have got the flow profile using these two codes. In the next lecture we will be talking about channel either in parallel or they will have more number of junction points or multiple channels connected there. Thank you.